Imagine signing a contract where every clause, including ones you'll never invoke, gets read aloud, photocopied, and billed to you. That's how Bitcoin's multi-condition scripts work today. Every branch, every backup key, every emergency clause hits the chain when you spend. A 25-year-old data structure quietly fixes all of it. It's called MAST. To see why this matters, look at what Bitcoin scripts do today. OPSIF is the conditional branching opcode. It lets a script offer multiple spending paths, a daily key, a code backup, a time-locked recovery clause. But OPIF carries three taxes. First, cost. Every branch you write adds bytes, and the bytes cost transaction fees, even if you never take that path. Second, the size cap. Legacy Bitcoin script tops out at 10,000 bytes. Even an entire block-sized script fits only about 20,000 branches. Third, privacy. The moment you spend, the whole script becomes public. Every cosigner, every condition, every backup. Observers see your full contingency plan. You're paying for branches you don't use, hitting a hard ceiling, and broadcasting your secrets. Compare them side by side. With OPIF, spending reveals the entire script. You pay bytes for every branch. You're capped at 10,000 bytes total. Every unused condition is exposed forever. With MAST, Merklized Alternative Script Trees, spending reveals one branch plus a tiny stack of hashes. You pay only for what you used. The size cap effectively vanishes. Unused branches stay completely hidden. Same security, same flexibility, dramatically less footprint. Merkle trees fix all three problems at once. Here's how. A Merkle tree is a hash structure that compresses a set into a single fingerprint. Start with leaves at the bottom. Each leaf is the hash of one item. Pair them up, hash each pair together, and you get the next level. Repeat until you reach a single 32-byte value at the top, the Merkle root. That root commits to every leaf. Change any leaf, and the root changes. Here's the crucial property. To prove that one specific leaf belongs in the tree, you only need that leaf plus the sibling hash at each level on the path to the root. Every other branch stays hidden. Anyone can verify the proof by rehashing up the path and checking it matches the root. Now apply this to Bitcoin. In MAST, each spending condition is a complete self-contained script. That script becomes a leaf. Hash all your possible scripts into a tree. The output commits only to the root. To spend, you reveal one script and the sibling hashes along its path. The network rehashes up to the root, confirms the commitment matches, and executes that single script. Everything else, every other clause, every other cosigner, every other time lock, stays mathematically committed but visually invisible. The cost scaling is the punchline. The number of hashes you reveal equals the ceiling of log base 2 of n, where n is your number of spending conditions. 3 conditions need 2 hashes, which is 64 bytes. 8 conditions need 3 hashes, 96 bytes. 15 hashes, just 480 bytes. Unlock 32,768 spending conditions. That's already 3 times more than a maximum-sized legacy script could ever fit. Push to 128 hashes, 4 kilobytes, and you commit to 2 to the 128th power conditions. Astronomical. Doubling your number of conditions adds exactly 1 hash. Cost grows logarithmically, not linearly. That is the MAST superpower. You can do even better with Huffman coding, a technique that places frequent items shallow and rare items deep. Put your everyday 2 of 3 multisig at depth 1, 1 hash to spend. Put your monthly code key recovery at depth 3. Put your 12-month time lock fallback, used almost never, at depth 5. Common spends pay almost nothing. Rare spends pay slightly more. Average fees plummet, and the tree shape itself stays hidden. And here's the privacy payoff. An observer watching the chain sees one revealed script and a few hashes. They cannot tell whether your tree had 1 leaf, 100 leaves, or 1 trillion. A simple wallet and an enterprise vault with thousands of contingency clauses produce identical-looking spans. The unused branches don't just stay private, their existence stays private. Once you can commit to 1 trillion conditions for the price of a few hashes, the design space cracks open. Vaults with layered recovery, inheritance schemes spanning decades, multi-party escrows with hundreds of arbitrators, contracts that were economically impossible become routine. A note on the name. MAST originally meant Merklized Abstract Syntax Tree, committing to every individual operation. The modern design switched to Merklized Alternative Script Tree, one whole script per leaf. Coarser but far more space efficient since you commit once per branch instead of once per opcode. MAST is a commitment scheme, not a smaller script. The unused branches still exist, they just never touch the chain. These ideas didn't stay theoretical. They became the foundation of Taproot, Bitcoin's production realization of Merkle committed scripts. That's where we go next.